So around a year ago, I decided I want to get a brand new red Tesla. I was pretty jealous of all my startup friends that were getting fresh Teslas from the same morning, but I had to buy my own Tesla. And not only did I need to buy my Tesla, I even had to get a loan in order to do so. So I did the natural thing. I approached my bank and asked for the loan. I was extremely surprised to learn that my loan was declined by the bank. I then approached them to ask why. Why did they decline my loan? And they responded saying that their black box credit score model decided that my income was way too low. Well, I'm a data scientist, so I asked them how the model came to this conclusion. Good afternoon, my name is Ben-Arie. I'm a principal data scientist at Intuit, and I'm extremely passionate about the topic of explainable AI. By the end of this 30-minute talk, I really hope that you will agree with me and all be passionate about it as well. The next day, I came back to the office and talked to my colleague, Yair, about my problem. We were both kind of worried that they may be using a concept called Gini importance in order to deduce the model's feature importance and tell me why my loan was declined. Now, Gini importance is the default method you get when you call XGBoost or random forest feature importance method, but it has its problems. You may not be aware of them even. I was worried because from my personal experience, there is a very strong bias in Gini importance towards continuous features. And as income is incredibly continuous, maybe this is the reason it was at the top of the list? Yair, on the other hand, wasn't sure their data scientists were capable enough of taking care of correlated features. And correlated features may also blur Gini importance's results. We were both talking and saying that we really hope they use SHAP because SHAP is currently considered to be best practice by many companies across the industry. And indeed, just a few hours later, I got this nice chart, which those of you that do use SHAP probably know and love, stating the feature importance for my case, and indeed, income topped the list. Besides this graph, I also received an extensive list of 100 model features, each with a respective Shapley value. SHAP is a method which is actually based on these Shapley values that were invented by Lloyd Shapley in the 50s. Shapley is an economist, and around 5 years ago, this method was translated as a method for model explainability. As I said before, I'm extremely passionate about XAI, which stands for Explainable AI, and I know all about the mathematical axioms that Shapley values satisfy. This made me feel a lot better because I knew what the system is. I was able to trust the fact that income is my problem. All I needed to do is take care of that, increase my income, and then I'll probably get my loan. By how much do I need to increase my income? Well, that's a story for another lecture. So fast forward 1 year, I moved to another company in order to increase my income. But my loan was still declined. Not only that, but now my credit score was even lower than last year's, and I just couldn't get a grasp on it. I couldn't understand how can that possibly be. Well, what I didn't tell you in the previous slide is that SHAP is an additive feature attribution approach, meaning it assigns a score or a weight to every single feature based on its marginal contribution towards the existing model prediction. But once one or more features change, there is no guarantee on what will happen to the model score. It does not allow what we call what-if analysis. And this is a problem. The story I just told you about my Tesla is not some imaginary scenario I made up. It's a reality day to day as data scientists around the world. Regulators all over are now addressing the right to explanation in their bills and acts. In the United States, the Equal Credit Opportunity Act states that we must give a statement of reasons for adverse actions, such as credit score declines. And these also must be very specific. In the European Union, the GDPR, which you may be well aware of, states that the end user has a right to obtain an explanation of the decision reached and even to challenge that decision. So now you understand that we really need to supply explanations for our model decisions. But what should a good explanation provide? This is not something trivial. Luckily, the GDPR gives us some clues. First and foremost, we need to inform the user and help him understand why a particular decision was reached. As I showed you before with SHAP, SHAP does this. SHAP gave me the information. I know that my income was the problem. But we also must provide grounds to contest. And we need to help the user understand what can be changed in order to receive the desired results using the same model. Points 2 and 3 are not addressed by the conventional feature importance or model explanation methods you are probably all using in your day-to-day work as data scientists. Luckily, in 2017, a fundamental paper was published addressing these requirements. This paper was the first to introduce the concept of counterfactual explanations formally, and it proved that these types of explanations are able to satisfy all 3 requirements above. So I gave some intuition regarding what counterfactuals are, but let's get a bit more formal. So a counterfactual explains a prediction by presenting a maximally close alternative input, but that would have resulted in a different, usually desired, prediction. And I'll show through an example. On the blue dots, on the left, we can see bank customers that got their loan rejected, just like I did. I am the light blue dot, marked as original input. In gray, we have the model's decision boundary, which means that, as you can guess, on the right, the orange dots are users that got their loan approved. So my goal is to explain my decision, the blue one, and to do this, I need to find the maximally close orange dot, the one marked here, and try to take a look at the differences between the original input and this counterfactual. So apparently there are only 2 differences between myself and the closest customer that got approved. This customer has an income that's $5,000 more than my income, and also has 1 more year of credit history. By comparing the 2, I can actually understand what I need to do in order to change the decision, and this orange dot is my counterfactual explanation. So now that we understand what counterfactuals are, let's talk about what makes a great counterfactual. Great counterfactuals have changes, right? We're talking about changes between the original input and the counterfactual, but these changes are limited to just a small subset of features. In the previous explanation, I showed that just changes in just 2 features are enough to flip the model decision. As we want the instance to be close to the counterfactual, we also need these changes to be slight and small. A more complicated thing to achieve is that we want the changes to be feasible and actionable. Offering a bank customer to reduce his age by 10 years is not something that's very doable, and this is something we need to avoid. On a technical side, as data scientists, we also need the counterfactuals to be standardized in order for us to be able to aggregate. I'll give an example. 1 counterfactual for 1 user is a great local explanation. But as we know, we also need to provide global explanations which explain how the model acts as a whole. And to do so, we need to aggregate over a large set of counterfactuals generated for a large number of instances or bank customers. So I hope you're pretty convinced that counterfactuals are good and that they're very simple to use and simple to read. Let me tell you that they are simple to use and read for many different audiences. A data scientist may want to use counterfactuals in order to get a sense of what the model decision landscape looks like. A policymaker, which is in charge of translating model scores into actions within the product, may want to use counterfactuals in order to analyze some false positives the model has. And an end customer, like the bank customer, may want to get counterfactuals in order to understand the decision and what can be done in order to change it. So I know it's late, but let's get a bit more technical as we are at Women in Data Science Conference and talk a bit about generation algorithms, or how can we actually generate these counterfactual explanations I discussed before. So I want to start off by saying that generating counterfactuals is not a trivial task. We demand so much from our counterfactuals. We want the counterfactual generator to be quick, efficient, and mathematically sound, so everyone, everywhere, can produce these explanations, even for real-time models. We also want the counterfactual generator to account for feasibility and actionability. Like I discussed before, we can't have explanations which a human can't follow. We also want our counterfactual generator to infer restrictions on its own. For example, to understand that age is a feature that has a specific range from 0 to 120 without having the user to input this manually every single time. And we also wanted to handle missing values, which we all have in our data, and categorical features, as our models do. The problem is that we want one algorithm that does it all, and this will be the optimal counterfactual generator. So let's start with a simple question. Why not select counterfactuals from existing data, for example, from our train sets, instead of generating synthetic counterfactuals, which is very difficult? Well, there are many problems with this approach. The first being that this actually will expose real customers' data, for example, bank customers. If an adversary, for example, will query counterfactuals 1 million times, with a good probability, he will end up attaining the entire train set, which is something we can't afford. Also, not every instance has this close neighbor, this counterfactual, an instance which is both close and received the opposite model prediction score. Well, this becomes even more prominent if we're talking about highly imbalanced data, because then the chance you will have a close neighbor which also received the opposite model prediction class becomes very, very low. So once we rule this out, we understand we actually need a generation approach, meaning we need an approach to generate synthetic counterfactuals for every instance from non-existing data. So let's start with the basics. The paper I talked about in 2017, which introduced the concept of counterfactuals, also gave us a great generation method. This method is very simple and is based on an approach you probably all know and use on a daily basis, which is minimizing a loss function. You can use any optimizer you want, and the loss function is actually pretty simple. Let's try to follow. The first term in the loss function is the distance between the model prediction for the counterfactual minus the desired outcome, meaning if my counterfactual received a model score of 0.6, but I would like to have a counterfactual with a score of 0.8, this term will be 0.2 squared. The second term is the distance between the original input features and the counterfactual features. And the third term is a balancing term that balances the two, the difference in the model prediction in the counterfactual versus the original input versus the distance in the features between the two. Note that this approach doesn't even require exposing the actual model. All we need is the original input we want to explain and access to get the model score through some API, which is great because we never want to give an external regulator access to our model. The problem with the minimization approach, with the loss function minimization approach I just showed you, is that it gives us only one single counterfactual per instance. But can there be more than one counterfactual? The answer is actually yes. There can be many different counterfactuals for a single instance. And DICE, or Diverse Counterfactual Explanations, by Microsoft is a paper and package which does exactly this. It uses a different generation method, which is called DPP, and it allows users to select the counterfactual they want to use from a large set of diverse counterfactuals. This approach of counterfactual diversity, or giving many different explanations for a single instance, is also good for us as data scientists and analysts because it can give us additional insights. For example, If we get 10 explanations, and in all explanations for that instance, we see that a single feature has to change, this says quite a lot regarding the feature importance of that specific feature, and we do this very simply. So back to my Tesla loan example, I actually advised the data scientists in the bank to use DICE and give me some diverse counterfactual explanations so I can finally understand what I can really do in order to get my loan approved. And indeed, I got 3 options from the bank, 3 diverse counterfactuals. So the first option is to have 3 more credit cards and increase my age by 1 year. The second option they gave me is to double my income. And the third option I got is to reduce my age by 4 years and also own a car. So let's try to understand what these counterfactuals mean to my actual life. The first is annoying. Increasing my age by a year means waiting a full year, but this is all pretty easy to do. Doubling my income is pretty complicated even as a talented data scientist in Israel these days. And the third option, well, that's not even feasible. I can't reduce my age by 4 years. And giving this explanation to an end user will probably make him end up not trusting your model and not trusting your explanations. This needs to be addressed. And sadly, this needs to be addressed by an external algorithm, as DICE isn't capable of doing this. Luckily, the same year DICE was published, an additional amazing algorithm was published as well. And this algorithm is called FACE. FACE stands for Feasible and Actionable Counterfactual Explanations. This algorithm is pretty complex, but I think I found a way to explain it through one single chart, which you see on your left. So let's start. In blue, the blue dots are bank customers that got their loan declined, like myself. I am this X. So these are the declined, this is the declined user space. On the right, we see the red dots, which are bank customers that got their loan approved, which is the favorable class. So the red area is the approval area, the blue is the decline area, and what we see in white here is the model's decision boundary. As I said, I am X, the declined customer, and I want to find feasible counterfactuals for myself. So the closest point is point A. Point A is indeed very close and also in the red area, which makes it a valid counterfactual. But is it a good option? No. A is way too close to the model decision boundary in order to be considered a robust and amazing explanation I would like to expose. So let's move to point B. Point B is a bit further, but it's also further in the red area, meaning there is a higher chance that this is a reasonable, stable choice for an approved customer. But the problem here is that B is in a sparse area, meaning there are no real bank customers that surround B. The authors of this paper claim that density is key to attaining feasible explanations. So let's move to point C. C is just as close, and it's in the red area, but it's also in a very dense area. C is close to real bank customers that got approved. This should make it an amazing counterfactual. But no. The authors claim that the best option is actually option D. And the reason is that to get from X to D, we pass only through dense areas, meaning every step along the way is dotted with real users. And if we follow the track of real users, there is a high probability that the entire path from X to D will also be feasible and something any person can follow. Great, so I just showed you 3 promising counterfactual generation methods, right? We talked about the loss function optimization technique. We talked about DICE, the diverse counterfactual package, and we talked about FACE, which generates only feasible and actionable counterfactuals. I'm sure you all want to run to the office tomorrow and try to produce counterfactuals for your own models. The only problem is that most of the recent advancements in the past 5 years in the field were purely academic. And actually, no user-friendly Python package comes with these amazing papers. There are a few that did come with great code, which is DICE, which we discussed before, the diverse counterfactual package, and Alibi, which we won't discuss today. The issue is that every author created a completely different package with completely different input formats, completely different restrictions, and completely different outputs. And this makes it extremely difficult to master all these different packages and practically impossible to compare and contrast the results of each of these techniques. Also, I tested DICE, the diverse counterfactual package, extensively on real-world data from my day-to-day work and was shocked to find numerous showstopper issues. I found that for 25% of my model's false positives, the package never converges, never. And also, it's unable to handle missing values and many more. And this caused me to understand that this package is not mature enough for my day-to-day use, not even to talk about my production models. This is a huge problem. But how can we fix it? So going back to SHAP, I personally attribute a lot of SHAP's success to its incredibly user-friendly Python package. I'm sure a lot of you use it in your day-to-day work, and you can see that it has so many stars and forks. So what if we had a framework, not just a package, but a full framework for counterfactual generation and analysis, which works with many different generation algorithms, even more than the three that I just discussed before, and is also simple to query, meaning we can also analyze the results using this framework. We all use different frameworks on a day-to-day basis. You probably know TensorFlow, PyTorch, NumPy, so why not have one for counterfactuals? And indeed, this is one of my top research interests. I'm part of Intuit's University Collaboration Program, and together with my colleague, Dr. Yair Choresh, Professor Daniel Deutsch, and Idan Meyuchas, we work together together with Tel Aviv University, to solve this problem and many more. Our paper, titled CFDB, Machine Learning Model Analysis via Databases of Counterfactuals, was actually recently accepted to ACM Sigma 2022. And the framework itself, the code is still work in progress, but I wanted to show you how it's going to work and how easy it is to use it as well. So as I said, our goal is to have a framework which users can use end-to-end for producing the counterfactuals and also analyzing them. And because our end users may be quite a varied audience, we can have data scientists and analysts, we selected SQL to be the language of choice. So the user inputs the instances and then tells us, inputs the instances and tells us which of them he would like to get counterfactuals for. We do the parsing, and then we dispatch the different counterfactual generators. This encapsulates the counterfactual generation in a way that the users don't need to worry about the differences between each and every one of them. And also, we can expand to different counterfactual generators as more and more become available and published. We then generate the counterfactuals and store them within a database, and we do several optimizations to make this very fast. And we return the results in a way that the end user can again use SQL to analyze and extract the insights for. So we're not going to go over the code, obviously, but I just wanted to show you how simple it's going to be to use our framework. So with just a few steps, the user can load the data, meaning the instances she or he wants to explain, and the models, then select the instances of interest she would like to explain. For example, many times you want to explain only the model's false positives. We can then select the counterfactual generator we would like to use. For example, here we have DICE, which you already know all about. And using this simple code, we can analyze and gain amazing insights from our generated counterfactuals. So you see so little code, and this is much easier than using all the existing frameworks. We can then execute the code and easily produce a chart. This chart, for example, compares 3 different classifiers, for example, classifiers trained over time, takes a look at 3 features and asks what is the feature importance of these 3 across the different models, taking into account only their false positives. This is a lot to grasp, I know, and the point is to explain that this complex query can be achieved in 30 lines of code. So besides usability and having a package, there are also many theoretical questions which are left for us to explore. I want to touch just 4 short questions now. The first is, how do we measure if a counterfactual explanation is good? This is a problem that's very prominent in the entire field of explainability. Measuring with one single metric if an explanation is good is not something that the data science or the research community knows how to answer today. Also, can a counterfactual always be generated for any instance? Or is there some even theoretical bound over this, which may mean that no, this isn't always possible? Also, what can we learn by tracking counterfactuals over time? Many of you probably retrain your models on a weekly or monthly basis, and I claim that using counterfactuals, you can learn a lot about what changes between the model variations, the model retrain variations, both on the model side and in the input data. And finally, my personal favorite is, can model robustness be estimated using counterfactual diversity? This is quite a complex question, and let me break it down. If we receive very indiverse explanations, meaning we generate hundreds of counterfactuals for hundreds of instances, and we see that they are very similar to each other, meaning there is just 1 or 2 features which, if we change, we can always flip the model decision by just that change. This can mean that an adversary attacker may also quickly learn that these 2 features can be changed to achieve anything he wants with a model. If we will be able to use counterfactuals to give a metric for model robustness, this will be a great advancement in the field, as this can be done even before the model goes to production. So just 30 minutes ago, I told you that by the end of this talk, I hope you will all be as passionate about explainable AI as I am. And now that you know all about counterfactuals, I hope that you would like to join me in exploring this fascinating field. You can do this in many ways. You can try the packages I talked about on your own data. Sure, they have their disadvantages, but maybe they'll work for you just fine. Also, in around 3 months, I hope we'll have an MVP version for our framework that you will be able to test out as well. You can contribute to open source. DICE, Microsoft's package, is actually an open source package, meaning you can all contribute and fix the issues I discussed before. And you can join in on academic research, like Yair and I do, through your company and through some collaboration program, or through your PhD studies maybe. And if we do all this, hopefully, someday, I'll be able to understand how to get my loan approved and finally get that Tesla. Thank you.